Section 8.4 is bond polarity, and the two bonding extremes are ionic and covalent, and there actually is a gradual transition in between. We're going to be using the values developed by Pauling, who was the double Nobel laureate, and what he did is he assigned a number to every element in the periodic table. What we'll see is that this scale is going to parallel ionization energy, and it's worth repeating, so I will. Here's the definition of electronegativity. It's the ability of an atom in a molecule to attract electrons to itself. Again, it is a relative scale. It's going to parallel ionization energy. And if we look at Pauling's scale, we will see that as we go from the left to the right, we're going to see the electronegativity increases. As we go down, it is going to decrease. So those are the two trends that will guide us. Now, in order to show you how it's applied, I chose three substances: sodium chloride, which is ionic, chlorine, the molecule, which is molecular, and HCl, which is HCl. All right, so what I did is I looked at the electronegativity table, and I saw that cation, sodium has a number 0.9, chlorine has a value 3.0. And yes, those are the ions, but we use the numbers for the atoms. I have to make myself clear. When I look at the difference between the two, that's what the delta is, I see here a 2.1. Let me kind of go a little bit further. I'm going to use chlorine's values again, and I'm going to see my difference now is equal to 0. Now I'm going to pump in the values for hydrogen and chlorine, and I see my difference is going to be 0.9. You notice there's a different word associated with these changes. Under a 2.1, I call it ionic. When I have a value of 0, I know it's a covalent bond. Those electrons are shared, but I also know that it is nonpolar. As for HCl, it doesn't have a value as big as ionic. It definitely is not a 0, so we're going to call it polar, and we're going to say covalent because we know the electrons are shared to form a bond. And that's essentially what it says in the bullets below. Notice, if it's a gas or a liquid, it's probably going to be more covalent. And if it's a solid, the bond is more ionic. So think about this. Sodium chloride, the solid. Think of something like water, a liquid at room temperature. It's going to be covalent. And they've had artists take a look at colors to help us see low and high electron densities. Now, one of the things you can do is calculate a number called the dipole moment. And what they show here is a negative charge and a positive charge. And they show a distance between that negative and positive charge. They say that the dipole moment mu is equal to Q times R. So there is our equation. I've used sample exercise 8.5 from your textbook for HCl. Here's the values you'd use in the calculation. The Q value, we'll use the value of the electron charge. We'll take an R of 1.27 angstroms, and what we really need is a conversion factor. How can we take the meters and coulombs and turn them into the dBi, which is what they use to measure a dipole moment? So all I'm doing is substituting in. I'm substituting in the value for Q. I'm substituting the value for R, and what I want in the long run is to have it terms of dBi. So I need a conversion factor here to take the angstroms to meters, and then I need the main conversion factor for that dBi, which has coulombs and meters. The coulombs will disappear, the meters will disappear. And what I'm left with is on the next page. I come up with a calculated dipole moment of 6.08 dBi. But if I go into the lab and I measure a dipole moment, I come up with a much smaller number, 1.08 dBi. So what people have to do is they have to talk about what's called the percent ionic character. I wrote down HCl. Yes, we say it is covalent, but now as we're using this idea, we see that the two values do not agree. So we will take our measured value of 1.08, We will take our calculated value of 6.08 and we will multiply it by 100. That will give us a percent ionic character of 17.8%. So HCl is not totally ionic, and I should say it is not totally covalent. It is at a level where you take a deeper look, a little bit of both. And what we normally do is we write that number as a decimal with a delta plus, or we write that number as a decimal with a delta minus by the element we're referring to. Now, this has always been a little bit confusing, so let's kind of give it a little more depth. What's the trend that we see? What we have are the halogens bonded to hydrogen here. What we have is their bond length, and as we look down this table, the bond length is definitely increasing. Let's look at the electronegativity difference. As we look at the electronegativity difference, what we see is that if we go down, the electronegativity difference is decreasing. Now let's look at the dipole moment as we go down. What we'll see is that that is also decreasing. So this is a trend. This is for the halogens. This is what we cover in Gen Chem. And what we say is that as the difference increases, our dipole moment is going to increase and our bond length is going to decrease. So when I discussed it above, I took it in a different direction. But what I'd like you to do is think about how you could apply each of those explanations to describe the trend we see here. And again, with the artist's rendition. Here we have HF, positive and negative based on the colors. And notice when we get HI, we do not see that large demarcation. This is all background for what we need to really have for Chapter 9. It's called molecular polarity. And what does polar mean? Well, if I have a positive and a negative, if their charges do not coincide, we say this is a polar species, and that is the symbolism that we give it. And notice what it says in the next line. If I have something called a polar molecule, it has opposite charges and they are separated by a distance. It has a dipole and it is measurable. It will not be a value of 0. So what do people do experimentally? Well, experimentally, they will measure the tendency for a molecule to line up in an electric field. If you've done electrophoresis in high school, or maybe you've done some here as a college student, you'll know what I'm talking about. And what number you get is called a dipole moment, symbolized by the letter mu, and its unit is a debye. So this is the background. These are the facts. This is the method that we use. Let's take a look at 3 different molecules. Before, when we looked at the change in electronegativity, we got a 0. When we put this into an electric field, the chlorine molecule, we see it has no dipole moment and we call it nonpolar. When we have HCl, well, my goodness, now we do have a dipole and it'll be somewhat polarized, all right? If I go from chlorine to fluorine, both of those are in S2P5, but fluorine has a higher electronegativity, it has a higher dipole moment, and it gets the name polar. This is like slightly polar. I mean, it's hard to really put names on these things. But what it definitely says to us is we are not always going to have equal electrons shared. They'll be shared equally when the atoms are alike in a bond, but if we're going to have different atoms, they will not be shared equally. So where does this fit? Well, in this section, we've just focused on a single bond. When we go on to Chapter 9, you will have actual molecules. We talked about HCl in this molecule, and that's the designation we give, and we say it's a polar molecule. We have ammonia, where we've got that lone pair of electrons. That's going to be a polar molecule. And another way we symbolize it is with an arrow and a plus sign. And you're doing a lab this semester, which is going to go into a lot more detail. Notice we see what's here, a tetrahedron. Notice here we see a flat planar. And notice here we see a polar. All of this will be explained when we do VSEPR and we talk about molecular geometry, okay, when we make these things be three-dimensional. So, how should you start to think as a general chemistry student? Well, if I have a molecule like ozone, each of these is an oxygen atom. I can measure the distance between these oxygen atoms, and I can also measure something called a bond angle, and we'll talk about those in Chapter 9. Later in this chapter, we're going to talk about resonance structures. That's what we have right down here. We're going to teach you how to draw them. And over on the right-hand side, again, is the artist's rendition. But the main idea here is if electrons are not shared equally, what we will have is a polarized bond. That can manifest itself by the measurement of a dipole moment.